Now we want to take the example of a sinusoidal wave and express mathematically how we say, is it traveling to the right or to the left. So we're not just going to have a static sine function, but one that's moving. We know that a wave function by itself at one particular time could look like a sine function, so sine of kx, but now we want to express mathematically how this thing moves. So let's suppose at time t equals 0 seconds, this is the wave function. F of x is a times sine of kx. We're going to say that that's y for all x at some time t equals 0, and I want to have y as a function of x and t. Let's suppose our particular wave is moving to the right. At time t1, the wave will have shifted by a distance d1, which is equal to velocity times t1. At time t2, the wave will have shifted by a distance d2, which is velocity times t2. And as time keeps growing, then the displacement of this traveling wave keeps moving further and further. If at time t equals 0, the wave function is given by y of x and 0 is equal to a sine of kx, then the way we create a traveling wave is to replace that variable x with the combination x minus vt. So just mentally, look at this x right here, cross it out, and put in x minus vt, and that's what I did in the next line down. Now I have the wave function for the traveling wave. It's a combination y of x and t, so it's a y, which is a function of both variables x and t, is a times the sine of k multiplying x minus vt. So there's a whole lot happening inside the argument of the sine function. Knowing what k is, I can replace that it's 2 pi over lambda. And now let's look at what happens at one particular location. In other words, I'm going to suppose that I'm in a buoy in the water at x equals 0. What do I see? Well, for x equals 0, I should plug in 0 right here for x, and wherever I see x in my argument of the sine function, I should plug in 0. And I have a times the sine of 2 pi over lambda vt. So I'm jiggling up and down as a function of time. My life buoy just goes up and down and up and down. After a time called the period, t, the traveling wave through the buoy has gone through one cycle. If I insert one period, t, into the argument of the sine function, then I should find that the argument goes back to being 2 pi, because I've gone through one full cycle. So I'm going to write that the argument of the sine function, which is 2 pi over lambda of velocity times this thing called the period, is equal to 2 pi. Another concept in oscillators is called the frequency, and it's the number of times per second that you go through an oscillation. I'll define the frequency, which is 1 over the period, for the wave as well. If I look at this, then I find out that there's a relationship. Velocity is wavelength times frequency for the wave, and that's true for all waves. So I can rewrite my original form for the expression of a traveling wave, y of x and t, is a times sine of the quantity kx minus omega t, where omega is 2 pi times the frequency. It's also sometimes called the angular frequency, or it's 2 pi over the period. This functional form right here in the red box, sine of kx minus omega t, is often given for the functional form of a traveling wave of a certain wavelength and a certain frequency.